Good morning. Welcome to our recording from Data Centre World London on sustainably powering mission critical data centre applications. I'm now going to pass over to Alex Ems from KOHLER Uninterruptible Power and Ian Wilcoxon from KOHLER Power Systems, who are going to talk through the presentation.
Thank you very much for the introduction. So, as it says there, we're going to talk about improving the environmental performance of critical power protection for data centre applications. So today, data centres are responsible for almost 1% of global electricity demand and about 1/3% of all global CO2 emissions. Of course, this brings into focus data centres, and without attention to sustainability measures, data centre operators may be prevented from growing. So developing new data centres, we've seen moratoriums in places such as Singapore, and of course there's similar discussions going on in Ireland. So data centre operators want cleaner critical power systems. Today, all power to critical loads passes through a UPS. They are permanently active, so a small difference in the efficiency has a significant impact on the energy usage and, of course, the cooling costs. In contrast, diesel generator sets in standby mode are not frequently used and are only responsible for a small percentage of the overall emissions. Nevertheless, generator set manufacturers like KOHLER are under pressure to develop more environmentally friendly solutions. And of course, we have envisioned the future where new approaches to standby power may come into play. So what does this mean for critical energy? Well, of course, we're looking at innovative new technologies, and they're being implemented in several fields. High efficiency UPS with things such as smart modes. UPS can be used, of course, for grid support and frequency support for the grid. A closer integration of the UPS and generator systems can result in smaller generator sizing. Of course, engine optimization for diesel generators with improved in-cylinder technology and after treatment. And of course, new approaches for more environmentally friendly maintenance. As KOHLER, we have developed a range of generator sets that are suitable for hydrotreated vegetable oil. And of course, there's some approaches with installations of multi-megawatt battery installs and hydrogen fuel cell research. Now I'm going to hand you over to Alex, who's going to talk about UPS systems.
Thanks, Ian. So yeah, the UPS system, obviously a very critical component for the data center for resilience and sustainability. When the UPS is there, main role is to smooth out the supply frequency and voltages disturbances over a very short time. And we see as main power grids depend more on renewable sources such as wind and solar power and less on the thermal power stations, it's expected that these grids will become more variable. So having that UPS in the system gives us the peace of mind that those variations will be removed before reaching sensitive equipment. Okay, and also, as Ian mentioned, the most modern UPSs can also provide a frequency support back to the grid itself. So what's been done to increase the efficiency and sustainability with UPSs? Now, over the years, the UPS designs have changed. Early days, we had transformer-based static or rotary UPSs, and their efficiency was quite often a lot less than 90%. Now, with the evolution of IGBTs, transistors, it allowed us to increase the switching technology, and therefore we was getting 95% going forward, and that was really increased once we get to the transformer static UPSs, pushing those bandwidths higher up towards the 95%. And those increases from sort of 90 to 95% meant, if we look at a figure of 1.5 megawatts for a 10-year saving, we're saving nearly 10 megawatts of power, megawatt hours of power. Electrical costs at today's prices, nearly 3,000 costs, and 4,500 tons of CO2 saved with that technology. Now, technology has moved on further. We've optimized interleave inverters, better layout onto the UPS, just designed around efficiency, using very high efficiency components, including the fans and devices. And this has increased efficiency over 97% with the highest and most efficient UPSs on the market. And looking at that 1.5 megawatts, that's a further increase of 4 megawatts in power, further increase in savings on the electrical cost, and of course, nearly another 2 tons of CO2. And so we can see that very small percentages in the efficiency does make a significant difference in the amount of power that we are wasting with the UPS. And then we wanted to sort of smart size the UPSs. Typically, UPSs will come as standalone monolithic systems. All the units have single unit components, so one inverter, one rectifier, one battery. And we have the modular systems where all the components are replicated, typically in slightly smaller modules. Now, what this means is when we're looking at a data center, we're always going to want redundancy, and typically N+1 redundancy. Now, if we were having the monolithic standalone systems, we would just add another unit on, potentially having an extra 100% extra UPS capacity. So instead of that, if you was doing it with the modular systems, the example shown, we would just add an extra module and just an extra 25% capacity, 75% less additional power infrastructure UPS than would have been done with the standalone monolithic types units. But these units, all units, will have operating bands for efficiency, and many UPSs are tuned for the best efficiency towards a mid power range on the basis that you are going to have redundancy in the system. But with any systems, the efficiency will drop off at low loads, and we can see here the most efficient band for this is about 40–50%, and it drops off significantly from 20% down. So what we want to do is keep those units running at their most efficient, and this is where the smart modes on UPS comes in, such as the extra VFI on the KOHLER UPS. We want to maintain redundancy, but also only have the units required to run as required. So in this example, we've got 20% of the rated load, so we're running 2 modules to give us redundancy. So we're running that at 40%. So that's in the most efficient band for those units. And with this mode, we've still got the 3 others in standby. So if the load increases, we need the capacity, or if we have one taken off for maintenance, for example, the others are there available to come on, keeping everything safe, secure, but also in the most efficient band for what they're designed for. So as Ian mentioned, frequency support can be provided from the UPS systems to help the mains grid. And there are different ways of doing the frequency support, as we know. Some of them are to backfeed the grid, some are behind the meter functionalities. But having that ability to deliver maybe just a few seconds of supply from frequency support can earn large money when you're available 100% of the time. And if you're doing it for short infrequent periods, this means it can be done even with the VRLA batteries, rather than having to go towards a cyclic lithium battery. So one of the big things that we look at and keeping everything right sized is utilizing the UPS systems to reduce the generator side. This is around the load acceptance. So typically with a legacy diesel generator, you would have a load step of 50–60%, followed by the final parts of the load to the 100% in around 7 seconds. The old legacy diesel generators are sort of high emissions and low fuel economy, but we're able to give that big load steps. Now, more modern engines with low emissions, typically the turbocharged set, have higher fuel economy, but they are built to an ISO standard, which means they are designed to have these smaller load steps. And we see an example here. So over the first 3 seconds of just 30% load step, another 30% load step, and 40%, stepping it in over 11 seconds rather than the 7 seconds. So the ISO standard, ISO 8528, outlines the requirements from the generator as a minimum. Okay, and this is what the modern engines are designed to meet. So we need to take that into account when we're actually designing the data center and the load acceptance. So, you know, we still get people requiring or asking for the 50 to 60% load step as the initial step. Okay, and this is, you know, legacy, and yes, everybody wants to get the load on as quickly as possible, as fast as possible in the least amount of steps. Now, what we should do is sort of look at the ISO standard. If you was to ask for that 50-60% load step at the beginning, with a modern engine that wouldn't be able to accept that, you'd have to increase the size of the generator to match. We got an example here of a 1 megawatt load. So 30% of that is, you know, 600 kilowatts. So we're potentially having to double the size of the generator to have that 60%, that 600 kilowatt load step initially. What we should be doing is looking at the whole power protection system as a whole. Okay, we have the UPS that will take the load during the mains failure, and when we transfer onto generator, the UPS will then transfer the power from the battery onto the generator in a very controlled manner, and typically it will be over sort of 30 seconds or more. So we're not worried that the generator can take the load in 7 seconds, you know, because the UPS will be maintaining that power and transferring it very, very gently onto the generator, well within the standards of the ISO requirements of the load steps. So this means we can very equally size the generator to the load, because we've got that UPS to take away the load steps that people are asking for. Okay, so we'll hand over to Ian now to talk about how these modern engines deliver.
Thanks for that, Alex. So let's have a deeper dive into the engine optimization. So today we have advanced in-cylinder arrangements using computer-aided engineering and computational fluid mechanics. This allows us to fine-tune the engine behavior, optimizing the entire system for better performance. Adjustments to piston and ring assembly tolerances. This reduces the amount of fuel escaping the combustion chamber, increasing the burn and efficiency of the engine. Of course, we have sophisticated engines with engine monitoring systems. We have common rail fuel systems, and this ensures that we have better fuel atomization and allows for fuel mapping on the combustion cycle, such that combustion is better tailored to emissions and reducing temperatures inside the cylinder. So, as we said, modern generators, we have highly optimized internal engine designs, and which you'll see in our KD series, but this also addresses something called wet stacking. So improvements reduce the need for artificial load while testing and enable data center operators to push out their maintenance schedules. Generator operators can conduct monthly generator tests now with no load instead of only performing an annual load test. These changes to the long-standing maintenance procedures allow significant fuel savings and reduce annual emissions by up to 85%, while complying, of course, to the relevant regulations. As well as the in-cylinder advances, we also have after-treatment technologies. We have things like diesel oxidation catalysts, which reduce CO2 and hydrocarbons. We have diesel particulate filters, which reduce things like soot and black smoke, and more and more we have a focus on selective catalytic reduction. Now this reduces the NOx emissions from an engine significantly and can be a reduction of up to 95%. As I touched on earlier, we also have renewable fuels, hydrotreated vegetable oil. This replaces regular diesel and can deliver up to 90% of lower carbon emissions without the need for engine modifications or additional fuel tanks. HVO can be mixed with regular diesel in any ratio without affecting the engine performance. And unlike previous generations of biofuels, HVO can be stored for many years without degrading, in fact up to 10 years without degrading. In Europe, it comes under the EN 15940 standard for diesel fuel. So HVO, what does it mean for data center sustainability? Well, it represents an immediate opportunity to reduce diesel engine emissions. Major HVO refineries are already operating in countries such as Holland, Italy, Sweden, France and Finland, which means it's widely available across Europe and in fact across the world. Co-location data center providers such as Interaction have begun swapping diesel for HVO to power its backup generators in France. In fact, KOHLER KD series engines in our factory in northern France are now tested and certified to run on a HVO 100 biofuel. Of course, as a company, we continue to analyse and assess newer types of cleaner fuels. So what are the technologies for the future? Longer-term commitments to eradicate hydrocarbons in data centres will result in the adoption of commercial scale solutions based on newer technologies. You know, we've seen installations of megawatt scale battery systems such as Google, where they installed a 2.75 megawatt lithium ion battery system, and that did replace some of the standby generators. It was also, whilst it reduced the emissions, it was also used to support the local electricity grid. But we need to consider in these types of installations the impact of producing and recycling of batteries. Of course, there is an alternative technology, and that's using hydrogen fuel cells. We've seen an installation with Microsoft where they were trialling an installation for Azure to support cloud servers, and that provided 48 hours of backup, and that used a 250 kilowatt hydrogen powered fuel cell. However, as hydrogen is clean at point of use, we really need to ask whether the source of the hydrogen is sustainable. So now I'm just going to hand you back over to Alex, and he's going to talk through the last couple of slides.
Thanks, Ian, again. Yes, so we can see that we have to deploy a sort of combination of technologies to look at this sustainability of our goals. So UPS systems are an essential component in protecting data centers, but high efficiency systems can also contribute to achieving our sustainability goals. We have alternative technologies now, such as the battery and fuel cell solutions, but these face significant scalability and cost challenges, as well as the sustainability challenges of that fuel and the batteries themselves. So neither of these newer technologies at the moment match the availability and energy density characteristics of a standby generator set, while sustainability varies. So future data centers will likely deploy a mix of backup power generation decided on a case-dependent basis, ensuring that performance, reliability and sustainability always go together. So in conclusion, the data center market continues to grow at a rapid pace, and sustainability is becoming a critical factor within it. These trends are driving the development and adoption of innovative technologies, particularly around the critical energy. Highly optimized UPS systems and generator sets are a fundamental part of securing increased sustainability now. Thanks for listening, and I hope you found that informative.